We have studied about the azimuthal quantum number and the principal quantum number, and we have started discussing about the magnetic quantum number. So, let us see. So, magnetic quantum number explained Zeeman effect and Stark effect. This was proposed by Alfred Landé, denoted by M, and this describes the orbitals. So, what is the definition for magnetic quantum number? So, they are orbitals, right? Orbitals indicate a three-dimensional space where the probability of finding an electron is maximum, and these three-dimensional space, that is the spatial orientation, is described with respect to the standard coordinate axis. Okay. So, there are three coordinate axes, x, y and z. With respect to these three coordinate axes, we will describe the probability of finding an electron in a 3D space. Okay. So, if azimuthal quantum number is L, that is L represents the subshells, then L will contain two L plus 1 orbitals, or better to say, each subshell contains 2L plus 1 orbitals. When we were discussing about the principal quantum number and azimuthal quantum number, we had said that each orbit contains n subshells, right? Now, each subshell contains 2L plus 1 orbitals, and the range of values are from minus L to plus L. Okay. So, let us say N, L, M and 2L plus 1. Okay. So, if N is equal to 1, then L will be 0. Now, what will be the number of orbitals in this subshell, that is the S subshell? So, 2 into 0 plus 1. So, this is 1. So, for the S subshell, there will be only one orbital, that is from minus L to plus L. 0 has no minus and plus. So, for here magnetic quantum number will also have the value of 0. Now, if n equal to 2, then the azimuthal numbers here can be 0 and 1. Now 0 means just one subshell. Okay, for S, this is S and this is P. For S subshell, we will have one orbital. For P subshell, P means 1. So 2 into 1 plus 1, that is 3 orbitals. So in total, n equal to 2, that is the second orbit, will have 4 orbitals. So for 0, we get m equal to 0. For 1, that is P, we get from minus L to plus L, right? So minus 1, here also we add 1 at every step starting from minus 1 till we reach, starting from minus L till we reach plus L. Okay, so we start from minus 1, then we add 1 to it, we get 0, then we add 1 again, we get plus 1. So there are 3 orbitals. Now these 3 orbitals, so P will have 3 orbitals, minus 1, 0 and plus 1. These 3 orbitals are arranged along the 3 axes, So the 3 axes are x, y, z, right? So we have 3 p orbitals called px, py and pz. Now since S had only one orbital, we denote S orbital by one box, or the S subshell by one box, that is one orbital. Since P has 3 orbitals, we denote like this, 3 boxes. Okay. Now if n is equal to 3, then what will be L? L will have, what will be the possible numbers? 0, 1 and 2. So m will be, for 0, this will be 0, that is for the S subshell. For the P subshell, m will be minus 1, 0, plus 1, right? So if we talk about the orbitals, then this is 3s. Now this is 3p. So 3p will have 3px, 3py, 3pz. And this one we were talking about n equal to 2. So here we will write 2px, 2py and 2pz. And here we will write 2s. This is 2s. And for this one, n equal to 1, we will write 1s. This is the way of writing the names of orbitals or denoting the orbitals. Now we have discussed about the p orbital. Now when n is equal to 3, we will have an extra azimuthal number, that is 2. This is called d subshell. Now what will be the values for d subshell? This is from minus L to plus L. So we will start with minus 2. We add 1 and we get -1, then we get 0, then +1, then +2. So, total of 5 orbitals. So, how we will calculate the number of orbitals? By 2l plus 1, d is 2. So, 2l plus 1 is equal to 2 into 2 plus 1. From here also we see that d subshell has 5 orbitals. Now, these are the 5 orbitals of d. With respect to the coordinate axis, we can write them as dxy, dyz, dxz, dx square minus y square and dz square. So, since there are 5 orbitals, d or subshell is denoted like this. So, -2, -1, 0, +1, +2. We write like this. So, for P, how we will write? -1, 0, +1, and for S it is 0. Okay. So, when the p orbitals were along the axis, the d orbitals will be between the axis, that is in the planes, between the axis. Now, if n is equal to 3, what will be the values of L? 0. First one is 0. So, let us see. 0 is S. M will have a value of 0. So, we get 3S. Okay. Now, L equal to 1. This is the p orbital. P orbital will have, p subshell will have 3 orbitals. So, here also we have -1, 0, +1. So, we get 3p. 3p will again have these 3 components. So, 3p. Now, for 2, it will be the d subshell which has -2, -1, 0, +1, +2. This is the 3D. We have discussed how there are 5 orbitals within D. So, and we write them like this. Okay. Now, if n is equal to 4, then for L equal to 0, we will have 0. This is 4S. For L equal to 1, we will have M equal to -1, 0, +1, that will be 4p with 3 orbitals. For L equal to 2, it will be -2, -1, 0, +1, +2, that is 4d with 5 orbitals. Okay. Now n equal to 4 will have L equal to 3 also. So if L equal to 3, then what will be the corresponding magnetic quantum numbers? So first let's calculate what will be the total number. 2L plus 1. So 2 into 3 plus 1, that is 7. So L equal to 3 means F subshell. So F subshell will have 7 orbitals. -3, -2, -1, 0, +1, +2, +3. Okay, these are the 7 orbitals of F. So we will write this like this. So we denote like this. Okay. Now the expressions of F orbitals are Fz cube, Fxz square, Fyz square, Fx into x square minus y square, Fy into x square minus y square, Fz into x square minus y square, and Fxyz. So these are the 7 orbitals of F. So we have discussed about the magnetic quantum number. Now the fourth one is spin quantum number. Which is S. We will discuss about the spin quantum number in the next lecture. Before that, let's do a little small question about the 3 quantum numbers that we have used so far. So the question is, using SPDF, describe the orbitals with following quantum numbers. So we have to tell the name of the orbital. Okay. The first question is n equal to 2, L equal to 0. So what is this? 2, 0 means S. So this is 2S. N equal to 4, L equal to 3. 3 means F. So this is 4F. N equal to 5, L equal to 2. 2 is D. So this is 5D. For N equal to 4, L equal to 1. 1 is P. So this is 4P. So now you can easily predict the names of the orbitals. Actually these are subshells, not orbitals, but the term subshell is a little rarely used. Mostly orbitals are used as a loose term. So in the next lecture we will discuss about the spin quantum number and the shapes and energies of these orbitals. Thank you.